This apparatus here we use in our Science of Acoustics labs to measure the speed of sound. What this is a resonance tube featuring a tube with an adjustable water level here. And what we do is we use this with a tuning fork of known frequency. In our lab we typically use a tuning fork of 1,000 hertz. What we instruct people is that you'll hear this tuning fork the loudest when the air column is an appropriate size. And for a tube that's open on the top and closed on the bottom, you can fit an odd number of quarter wavelengths in that space for a resonant standing wave. Now, I should mention that the measurement on the tube here in centimeters is not perfectly the length of the pipe. The pipe has an effective length which is slightly longer depending on the width of the tube, so that will introduce a little bit of error into the proceedings unless you explicitly account for it. But let me at least show off what the phenomenon is going to be. If you play a tuning fork here and drop the water level, you should have heard there, hopefully, go the other way. There's a moment going each way where the sound is the loudest. At that level, that's where you have the best standing wave resonance going on. Now for me, that happens typically between 7 or 8 centimeters with this pipe. And you can verify that going in either direction. I'll start a little lower and go up. There was the little volume swell there when the length of air column was between 7 and 8 centimeters. Here's an up-close view of what's going to be happening with the tube, and you can observe by raising and lowering this reservoir of water. I can adjust the level. Hopefully you'll be able to see here that somewhere around 7 or 8 centimeters, the tuning fork vibrations will be the loudest. So, like I mentioned before, the width of the pipe here adds a little bit of length to the effective length of the tube. That effect is largest for this one, so if you do a speed of sound measurement strictly with this, you're probably going to get the least accurate results with that. But knowing that the first quarter wave fit within about 7 or 8 centimeters, that tells me the next standing wave that'll fit will be about 3/4 of a wavelength. So at approximately triple that distance, so somewhere a little further down here on the pipe, actually you'll be able to hear the volume swell again once the length becomes appropriate for that. So I'm going to start higher. I'll do this again. You'll be able to hear the sound get louder around here, and then again further down. That was one. And that was the second one. Maybe you could hear that faintly. I'll start again and go the other direction so you can see exactly where that happened. So for me, that occurred around 24 or 25 centimeters. And of course, in the lab, you want to measure that more carefully. But what that measurement will give you approximately is 3/4 of the wavelength. And you can get another data point further down at 5/4 the wavelength as well. So as long as you know the frequency and you can measure where these resonant spots are, you can measure the speed of sound with this apparatus.